Hey, what's up? Welcome to my practice stream. So this is a math practice channel. My name is John. If it's your first time here, welcome. It's wonderful to have you. Today we're going to be solving problems from these two books, Calculus and this Ordinary Differential Equations book. I've pretty much never even opened this, but it looks really nice. It's a Dover book. It's very cheap, and it looks really nice. So over the last few practice sessions, we've been doing problems from Taalman, and this is an incredible book. I'm very, very happy that one of my students that I'm tutoring showed me this book. It's really nice. So over the last couple of streams, we've introduced the limit. I showed how wildly different the limit is in theoretical mathematics. And today I want to be getting into some actual applied mathematics. I want to get to Mars, y'all. Like Earth, I don't feel good about the future of Earth. We got to get to Mars. And if I understand correctly, this book is going to help us get to Mars. So we're going to pull up the iPad and solve a bunch of problems. But first, I want to tell a nice little story. This channel is growing. I mean, it's brand new. This is like the second 2.5 weeks, something like that. Really, I started it essentially this year in January, and it's January 17th, so it's like barely 2 weeks, 2.5. And 222 subscribers at the moment. Thank you all for subscribing. Not too many comments in the comment section, but we do have a few regulars in the chat, in the practice during the stream, so that's to me even more important. And in the title, I've got a funny little story, I guess. Yesterday, let me pull it up so I know exactly the phrasing of it. This makes me really happy. I'm gonna brag with y'all for just a second here. Where is it? Yeah, okay. So, friend of the channel. I won't say your name right now because I don't know if you're going to be embarrassed by this story or not, but this person writes, subject, looking for a mentor. Hello, professor. My name is da-da-da. I found you on YouTube. I have an interest in math and AI. I'm just going to summarize. I can't afford college right now, but I would love some pointers of resources so that I can continue mathematics and study AI. And that's a summary. And so, yeah, sure, whatever. I'll be your mentor. Like, why not? Yeah, I don't care. Show up. If you show up in the chat, I'm happy to answer any math questions you might have. I want to build a cool, fun little community here of people helping each other study math and give pointers to other math channels, to textbooks, and we're going to be solving a lot of problems here. If you want to solve problems with me, just pause the damn video and try to solve it yourself before I get into my solutions, right? So yeah, sure, whatever. I'll be your mentor. I'm not going to do it privately. That costs money. I am available. themathhobbyist@gmail.com is somewhere below me. I am available for private tutoring, but that costs money, I'm sorry. But if you want to help me build up this channel, that's great. Hell yeah, I'll be your mentor. But yeah, that was funny. So I started just drafting my reply, and then I noticed I'm not the only one in the to field. There's also a couple of other huge, amazing YouTubers. First is, I don't even know how to pronounce it, DBOs. I'll link their channels at some point if I remember to. But I've seen the thumbnails from this. I think it's two people. I don't really remember. DIBEOS. And I think that they have 100,000 subs or something when I looked last night. And I have seen one video. I finally clicked on one, and it was an amazing story about Ramanujan. Highly produced, excellent YouTube tutorial, very kind of YouTube-y, not raw and unedited like this practice stream. So I was like, okay, that's cool. All right. So they were number one in the two field. Number 2 was me. So I was number 2. And then what threw me for a loop is I saw that the third one had math.berkeley.edu as the email. And I was just like, REB, I think I know, I've seen that before. And so I Googled that and I was like, oh, holy fuck, this is Richard BORCHERDS. This person put Richard BORCHERDS beneath me and DBOs. No. You do not put Richard BORCHERDS in the same recipient field as anybody else. You send Professor BORCHERDS his own email. Do not even pretend that you're emailing anybody else. And if you do include other people, for whatever reason, you put him first. Okay? Next time, anybody out there, anybody watching this, if you are emailing both me and Professor BORCHERDS, you put BORCHERDS first. Let's be clear about that. So for those who don't know, mathematics doesn't have a Nobel Prize. We have, the closest thing is the Fields Medal, and there's some sort of folktale that the person who invented the Nobel Prize was really mad at a mathematician for his wife cheating on him with a mathematician. That's like probably false. That's probably not a true story, but for whatever reason, mathematics has never been part of the Nobel Prize. So we have our own special alternative called the Fields Medal, and Professor BORCHERDS is a Fields medalist. So we're talking about like a Nobel Prize. You put a Nobel Prize winner essentially after me. So that, no, we gotta fix that. But anyways, yeah, so that's the title. I hope it got you to click, because I want to build a cool little community here. All right. Yeah, so this person's seeking a mentor. Hopefully we can help you out here in the chat or in the comment section. And I'll, like, why not? Here's my opportunity. I'm also looking for a mentor. If anybody wants to help me out, I'd love to get back into more proof-based mathematics and have somebody to be able to ask questions to. So if that sounds fun, just comment in the comment section or in the chat. And yeah, let's, mentors all the way down, like turtles all the way down, mentors all the way down. Let's build a cool community, y'all. All right, let's get into actual math instead of stupid vloggy me yapping. Like, who cares what I have to say? Let's get to the real stuff. Let's get to some math. So over the last couple of sessions, we've introduced the limit, and I just want to like rip straight to the fun stuff. Today I'm going to quickly define the derivative. I'm going to state a couple of properties about it, and then we're going to solve a couple of differential equations. As I understand it, this book is going to help us get to Mars, whereas I don't have it on me. Where is it? The other books that we've been doing, these are beautiful books. This is the kind of math that I studied 15 years ago when I did a mathematics degree. I did take a couple of differential equations courses, but I didn't really specialize in this. I was more interested in this type of math. This is like playing a beautiful but useless game of chess. It's beautiful, it is worth it, it will stretch your mind, it is so wonderful, but it's kind of useless. Like, kind of on purpose. Kind of intentionally, this stuff is sort of useless. This one is going to solve real-world problems, and in the positive case, we get to Mars. In the negative case, we can create some evil stuff. So, let's get into it. I'm going to try to give my own hobbyist definition of the derivative, and then we'll check Taalman and see how close I was. Also, we got a couple people in chat. Sam, good day, sir. RK9 Gaming, hello, folks. Thank you for tuning in. It's great to see y'all. How are you? What kind of math are you studying today? What's going on? How was that? How was that video intro? Did you find that enjoyable? Let me. Oops, wrong one. iPad horizontal, and then for whatever reason, I always have to double click this thing. Okay, so we've been solving a bunch of problems. We did a lot of problems from Taalman yesterday. We've been solving all these problems about limits. I haven't done too many problems on the formal definition of a limit, again, because that is, that's like playing chess. It's so beautiful. It is so worth it, but, it's kind of pointless. How differential equations originate. I've written in this little problem thing from Tenenbaum and Pollard, and we're going to finally get started on that stuff. Keanu dude, hi, how's it going? RK9, I'm still at the basics of math, cool. So I'll mention, I have been doing 7 streams in a row per subject, but I think I'm going to change that. Saturdays are going to be SAT Saturdays. And so I'll be solving some more basic level math. So no worries if you're not following along. Hopefully this is still enjoyable, even if you don't know what the hell is going on. I hope that we can create kind of like a study group, that's still enjoyable. All right, so I wrote out a bunch of Tenenbaum problems. And so we can get a sense of like what are we working toward here? What are we trying to understand? And Taalman had a couple of problems that were sort of similar, like in the applications sections, which were super cool. Really love them. Today I'm going to be reading Tenenbaum section 1.1, and here's a couple of problems that we're going to apparently be able to solve. The radium in a piece of lead decomposes at a rate which is proportional to the amount present. If 10% of the radium decomposes in 200 years, what percent of the original amount of radium will be present in a piece of lead after 1,000 years? All right, so right out the gate, the mathematician's just calling out the engineers. Let's duplicate that. Because I like how I wrote these things out. All right, so we got radium. Just right out the gate, we're calling out the engineers. Thanks for turning something beautiful and creating nuclear weapons out of it. So radium decomposing 10% after 200 years. What percent will be present after 1,000 years? Okay, well, I'm going to have to read a little bit of the section to make sure, but it looks like maybe if it's proportional, is it linearly proportional? And I can just take 2 points, like if 10% decomposed in 200 years, what percent will be present after 1,000 years? So we could try to imagine that it might be a line with a negative slope. I don't think that that's going to be true. I think that it's going to look more like an exponential decaying function. And after 200 years, we have so much. And then after 1,000 years, we have less, but still some. I'm going to guess that the section is going to define this decaying function, like e to the negative t, probably with some sort of constant or something, e to the negative rt. I bet this is what we're going to get. I don't remember. It's been a long time. Some other problems. Assume that the half-life of the radium in a piece of lead is 1,600 years. Okay, so reading again, half-life means 50%. 50% is Half-Life. Half-Life is also a cool video game. I think about nuclear weapons as well. So half-life in a piece of lead is 1,600 years. So I think that we're going to be solving some sort of equation like y equals e to the negative rt, and we have like half of the total amount, I don't know, 0. Really, yeah, let's just say half equals e to the negative r times t being in years 1600, and 1% at e to the negative r times 0. Is this how it goes? I think we need like a constant in front, a constant. I have no idea. We'll find out. I'll read the section. I'll remind myself how this works. But we are trying to get to this type of math. The following item appeared in a newspaper. The expedition used the carbon-14 test to measure the amount of radioactivity still present in the organic material found in the ruins, thereby determining that a town existed there as long ago as 7,000 BC. Using the half-life figure of C14 as given in the text, so we'll learn about what C14 is, determine the approximate percentage of C14 still present at the time of discovery. Okay, that sounds cool. So here we have a couple of problems about radium just right out the gate. And then we have one that's about discovering the origins of humanity and ancient civilizations of 7,000 BC. So this one's a little bit more positive, I feel, of a problem. And this one's I don't know about this. I don't know about this. Cool. So lesson 1 from Tenenbaum is going to be about how differential equations originate. It's going to be studying and learning a little bit about why are we going to learn about differential equations. Then lesson 2 is going to be a little bit more just mathy and it's going to be more foundational, studying functions and just defining functions and things like set and function. That's just like Taalman's 0.1. So I'll just quickly do those problems, or maybe not at all. And then 1.2.2 is also similar or boring or something. Then we're going to get to lesson 3, and now we're going to start talking about differential equations. Okay, so in order to get here, we need to define what y apostrophe means, and what does d2y over dx squared, what does that mean? And then similarly in 1.4, show that each of the functions on the left is a solution to the equation on the right. So in some sense, if we plug in y into this other equation, we should see that it satisfies the second equation. That's what we're looking for. So this is where we're going to be headed. Cool. And before I get to it, because I see in my retention graphs, I lose 90% of the viewers in the first 30 seconds. So if you are still here, if you enjoy this stuff, you can buy me a coffee by going to thanks.themathhobbyist.com. And you can also email me and just say thanks. That doesn't cost you anything. But if you enjoy this, just let me know. In the comment section is the best. But if you just send a nice note to this email, that also means a lot to me, and it keeps me going. So that's 2 ways that you can say thanks for this content. And it tells me to just keep doing this. Cool. RK9 Gaming. So tell me, still at the basics of math, what kind of math? What are you studying now? Are you in high school? Like, are you studying functions yet? Or do you know what the word domain means? Let us know if you get stuck on any problems, and we'd be happy to help you out. How about that? All right, cool. So that's where we're working toward. We're going to be solving some differential equations, so we need to know what is a derivative. That, spoiler, that is what we need. Cool. So, what is today? Day 6. Relearning calculus as an ex-Googler. I hate using that title, but you know, it is attention grabbing, and I'm proud of it. I'm proud of the fact that I worked at Google. Cool. So, goal: solve a Notorious ODE. What do we need to get there? We need the definition of a derivative. And we need some properties. So I will state without proof a couple of those properties, and maybe in the future, I'm sure that in the future, we will prove some of those properties. But just for today, we're just going to define a derivative, there it is. State a couple of properties without proof, and then we can solve an ODE. Okay, so what the hell is a derivative? Math hobbyist definition is going to be the derivative henceforth dy dx or y prime. These are two different notations for the derivative of a function. The derivative of a function is another function such that it, quote unquote, measures an instantaneous rate of change. Formally, dy dx equals, it's a separate function, and again, we can use a prime, or we can write this as dy dx, but it's given a function f, we transform it to another function f prime. So the derivative in some sense is like a transformation of functions. And yeah, it is the limit. So this is what we were doing yesterday. As h tends to 0 of f of x plus h minus f of x divided by h. Okay, so what does this mean? Why is this an instantaneous rate of change? It's because this, we learned earlier that the average rate of change in Taalman's book, in section 1.1, I think, or in section 0.1, I believe, on an interval between A to B, say that we have a curve, and we're interested in the rate of change between A, 2 points, A and B, then, I don't know, blue? Let's use blue. What we can do is we can take the value at those 2 points, and we can draw the line that connects them. We had a couple of problems that did this. So between those 2 points, like, you can approximate this function, and you can see that this line kind of looks like that function if you take 2 sample points and you just pretend that the curvy function is a line instead, right? So that's like a linear approximation of the function using the interval a comma b. Now, what happens if we took this exact same function, if we duplicate this thing, and then what if we made a and b smaller? Like, what if we put b way closer to a? I'm not going to get too fancy here, although I'm tempted to just move b just to show that, but it's not worth it. Okay, so what happens if we move b way closer? Like, maybe it's here instead. Maybe roughly a little bit more than halfway closer. Then the line that connects the two looks more like this, right? Okay, that's cool. What if we make it super duper close? Super freaking close. Then we get the same function if we erase the line that we created. I love this app. This app is so great. Like, it's so cool to be able to draw exactly the same function 3 times without, by just copying. Okay, so what if we put b very close? Right? So then this point B is right here. Okay. As we're getting closer and closer, all 3 of those slopes look kind of similar. Those lines don't look that wildly different, actually. And that's an accident. But eventually, if you keep doing that, and then you take the limit as the distance between those points, again, we have a limit, as the limit of those 2 points comes to 0, so they're as close as possible to each other, then you have the derivative at a point. How is that explanation? It sounds like a hobbyist just tried to define something complicated. All of this whole channel, do not learn from me, y'all. All right, so if it's only at that one point, it is going to perfectly be like, now I'm just going to call it, well, let's just keep using A. So now this is the derivative of the function evaluated at the point A. It's like a slope of a tangent line. Yeah, the slope of a tangent line that only touches the function at that one point. Hey, when is the Guitar Lift review coming? It's coming soon. I struggled a little bit to install it. Yeah, I just haven't gotten around to it yet. But it will happen soon. Good to see you, G Guy. G Guy in the chat is asking about my guitar channel and a guitar stream that I do, and my first ever piece of merchandise, my first ever brand deal that I've ever gotten as a content creator. So yeah, that is coming soon. So far, I'm not sure if it's going to work for me, to be perfectly honest, but I hope it does. I'm going to figure it out. I think I'm going to try to install it and get it to the perfect position with my teacher in person sometime. Good to see you, though. Thanks for stopping by. Okay, so there is my there's my attempt at, like, why do we have a limit h tending to 0 f of x plus h minus f of x divided by h. This you can think of as a change in y over a change in x. Because here, if the point B is x plus h in my other notation, and a, so like this interval a to b keeps shrinking. This interval is a to a plus some distance after it, a plus h. And then here, h, well, that is going to be, remember, rise over run. The denominator is, like, change of x is the second y value, or the second x value, which is x plus h, minus the first x value. And, well, x plus h minus x is just the change in x. Yeah, change is hard. Speaking of change, change is hard. I hope that I can switch over, because I've heard nothing but good things about that guitar support. Okay, so there's like a little bit of intuition for why we define the derivative this way. And again, all we really need, like the heavy machinery that we need in order to define this thing, is the idea of a limit. So a lot of people think that calculus, like the derivative, is the most important idea in calculus. You think of the derivative, d by dx, and you think of the integral, which, sneak peek, that's like the opposite of the derivative, and we will find it later. A lot of people think of those as the most important idea in calculus, but both of them depend on this idea of limits. So I don't know, like, how do you choose between your favorite children? They're both important. I'm not going to say that one's more important than the other, but limit is as important, I would say. It's as important as the idea of the derivative or the idea of the integral, the antiderivative. Okay. So that was my definition. Now let's give a reaction to Taalman. How does Taalman define it? And I don't even know what chapter or whatever this is going to be. Let's just find out. Oh, how's it going, G guy? What's going on with you? How are you? All right, so I think all of chapter 1 is about limits, and there are several sections. Yeah, there are like, infinite limits and indeterminate forms. That's so cool. Okay, so Taalman's book defines indeterminate forms before... Yeah, okay, cool. Taalman defines indeterminate forms before defining the derivative, like in the chapter where you learn about limits. I love that. So in math, briefly, let's give a little note. In section 1.5, Taalman introduces indeterminate forms. All right, so we all know that you can't divide by 0, right? So like any number divided by 0 is undefined. But guess what? If you have a limit that approaches something like 0 over 0, this can be defined. For example, if you think of x squared over x, this is our trusty old line with a hole in it. This line is undefined at the point 0 because you can't, again, divide by 0. So it's not defined at 0, but I think that we can all see that the slope, like the limit, should equal 1 because like the slope of this line is 1 everywhere. Like if you think of as you get infinitely close to that... Oh, wait, no, sorry, I'm mixing up ideas. The limit of our function, like infinitely close to the point 0, the limit should be 0. Like, and we saw this example in the limits section a couple of days ago, and I think that we proved it. I believe we can prove that the limit is 0, even though this function is kind of tending to 0 over 0. So, in some real sense, you're not allowed to divide by 0, but you can do 0 divided by 0 in math. You can also find things like, a raised to the 0 is 1, usually, but then 0 raised to the a is always 0. So something's wrong, we need to fix this. Anytime that a is not 0, we always have that first thing that's always true. And anytime that a is not equal to 0, in this one, 0 raised to the a is 0. So what happens if you have something like 0 raised to the 0, or we also have what if you have something like infinity raised to the 0, or infinity raised to infinity? like these are all indeterminate forms where you can find a limit even as some of these things. Well, this one, I think that one would tend to, that one always needs to tend to infinity. But like, what if you had infinity raised to the negative infinity? You have like a function that looks something like that. Like on the one hand, the base is going up, but then the denominator is causing it to decay. You can find limits of these indeterminate forms. So that's kind of cool. It's like you learn for a long time that you can't divide by 0, but there are times that you can sort of divide by 0. Anyways, there's my reaction. Definition of derivative according to Taalman. Yeah, so she uses tangent lines, she uses slopes, heights, approximating the slope of a tangent line, approximating instantaneous rate of change. So she used the exact same term that I did, instantaneous rate of change. Graphing a velocity of something. Where's our Oh. Okay. All right, so in section 2.1, there's no definition. It's just intuition. And it's a bunch of examples of instantaneous rate of change. And then again, 2.2, she does the formal as opposed to an intuitive introduction. A formal definition of a derivative. The derivative at x equals c of a function f is the number f prime at c, which is limit as h. Hey, she uses h2. That's good. Okay. Okay. Cool. So I remembered some pretty simple things, similar things, but I missed a couple of details. So I will give my reaction to that, provided that this limit exists. So I missed a couple of fine details here. She uses the point C and makes that very clear, whereas what I did is I wrote f prime at x. So what I like about her is that making it clear that this is at a single point, x equals c, removes the assumption or the connotation that this function is defined at all, or that it's defined at every point x. Like if f is defined at x, I don't think that implies that f prime is defined at x. It definitely does not imply that that the derivative is defined at x. So I do like that she defined the derivative at a point. that was the right way to do it. Whereas I was immediately jumping to another function, and I was implying that that function would be defined for all of the same domain. So that was incorrect on my part, but I was pretty close. And I like that she also called it out that explicitly you can think of it like equivalently. We have this change of y over change of x, the same way that I showed this example of the rate of change between 2 points A and B. So here, this is like change of y over change of x. This is the other formulation, and these two are equivalent, as I tried to show. And then, again, yeah, provided that this limit exists. It is way more precise to state that. I did not state that that this limit exists. So, yeah, or that this limit may not exist. I didn't call that out directly. So that's great, but I got the basic shape of this definition. That's cool. Okay, so there's a definition of a derivative, and I'm going to skip forward. Oh, okay. So this is the definition of the derivative of a function at a point. Derivative of a function at a point. And that, just so that we know, is definition 2.2. Then Taalman very clearly, very cleanly defines 2.3 differentiability. Like, what do you mean by differentiability? What does that term mean at a point? So Taalman's book is like very organized and clear and shows like the logical structure of definitions, theorems, proofs in a freshman calculus book, which is so cool to me. Differentiability at a point, a function f is differentiable at x equals c if limit as h tends to 0, c plus h minus f of c divided by h exists. So, I mean, I find this a little interesting. I would do it differently because all of this content is exactly the same as the derivative of a function at a point. I would have reused the prior definition. The function f is differentiable at x equals c if the derivative of f exists at c or something. And in fact, I would have put that in this same definition, 2.2, like provided that this limit exists, comma, in which case we say f is differentiable at x equals c. I would have just put that extra little definition in this definition 2.2. But it's kind of a style thing. Like if you want every underlined term to get its own special yellow box, I guess it makes sense. But to me, that's just like ever so slightly more formal than it's helpful. I'm going to just say that Taalman defines the one-sided differentiability at a point. That's interesting. I haven't seen that as often in like a freshman calculus. This is cool. This is really, yeah, I do want to write this. There's like some words above, but here's like the equation, and you can imagine what the words say. H tends to 0 from, why 0? Oh yeah, H tends to 0 from the left, f of c plus h minus f of c over h. And we have the derivative from the right at a point. So, yeah, basically it's the definitions of the derivative function with one-sided limits, just like we saw one-sided limits in the other video, in the other stream, practice stream. These are not lectures, y'all. Please do not call me a teacher or a lecturer or anything like that. These are practice sessions, y'all. Okay, then Taalman gives a theorem. A theorem is a statement that we can prove to be true, not something that we just make up and invent. Differentiability implies continuity. And I'm going to skip writing that out, skip the proof. Theorem 2.6, we have equation of the tangent line to a function at a point. Okay, cool. So I stated, without any kind of proof, that I stated that like the derivative can be thought of as the slope of the tangent line at a point. But notice that I did it the same way. I said formally, here is the definition of the derivative, and then I said you can think of it this way. Right? So Taalman is showing as a theorem, as a proof, she's proving why you can think of it this way. And I think that the proof is going to be basically exactly what I'm doing here. Like, think of a single point being like the change of x being instantaneously small. Yeah. Like, I bet that the proof is going to be something like what I was saying in words. What I was saying super confusingly. All right, what am I trying to get to again? I feel like there's something I wanted. Definition 2.7, we're getting to some other territory I don't need, I feel. Local linearity. We have a bunch of words, and then we have this thing. F of x is approximately equal to f of c plus the derivative at that point times x minus c. And that's kind of like how I was saying that we could approximate this function as the point at A. Yeah, we can approximate this function as that line, like, and that it's kind of a terrible approximation. We can see that this curve is very curvy and slopes way upward, and we're getting like a lot of error as we move away from that point. But it's still like a really, rough approximation. And within this small interval, hey, it's not bad. It's like, the error is very small. So that approximation is close, near the point A. But then as you zoom out, these error terms are getting much, much bigger, right? So that is a theorem, or no, a definition. Leibniz notation is next. Leibniz notation. These two were frenemies. Leibniz and Newton both invented calculus at the same time, and they argued. People argue who invented it first, and who copied who. But Leibniz notation is like dy dx or df dx, and it is meant to be like change of y over change of x as d gets really small. Like, that's kind of why we use that that notation. Like, that triangle is delta. And if delta is really small, then we don't write ELTA, we just write D. That's like a small delta. I'm making this up. So Leibniz notation would have something like df dx evaluated at the point 3 equals 6, for example. And we will use the two interchangeably. This is the same as saying y prime at 3 equals 6, or something like that. You with me? Okay, so we have some examples of calculations. And then in the next section we get some basic rules, and this is what I wanted to get to. Theorem 2.8. She says derivatives of constant, identity, and linear functions. I'm going to say simple derivatives, part 1. The derivative of a number is 0. I'm not going to do the proofs today. Maybe we will in the future. But I think that we can see if the function is y equals k, the slope is always 0 everywhere, right? So that seems to make sense. And we could do it by running through the definition, but we'll get there. D dx of the derivative of the line y equals x, well, that always has slope 1. The slope is 1 at every single point. And then the derivative of mx plus b is m. So this is very similar. It's just that this line is moved somewhere else. So maybe the line is going down instead. But everywhere the slope is written as m, and it's rise over run, change of y over change of x. And the slope is always the same in a line at every point. So these should be pretty straightforward and easy to prove. And you could try to do it yourself if you want to imagine, or if you want to try to take the definition of a derivative. So you will use this definition and try to, like, when you use these functions, f, really mx plus b is the only one that you really need to do, because then the other two follow. Parts A and B follow if you can prove mx plus b, because these are also lines. It's just that one is a constant value line, and then the other one is the line with slope 1 and intercept 0. So if you prove this one, that implies B, and it also implies A. So if you're lazy like me, you can just prove that one part that's necessary. But I'm going to keep going. Power rule. Theorem 2.9. Power rule. Also, I think that most people who are still watching this video at this point, you already know all this stuff. This is probably not your first time learning calculus. Drop a comment in the comment section if you haven't seen this before and you still enjoy this video. Please let me know, because I get the feeling that most of my audience is grad students at this point, or at least people who have done Calc 2. But yeah, if you are still watching this video and enjoying it, and you're learning this for the first time, drop a comment and let me know if I'm moving too fast or if you're still with me. Theorem 2.9, power rule. For any non-zero rational number k, d dx x to the k is equal to k x k minus 1. This is not hard to prove either. You can do it. I believe in you. You can do this. Try proving it at home for yourself. I think you can do it. And it's pretty cool. Yeah, so when k is not 0, that was important. So why, okay, for any non-zero rational number k, do we need k to be rational? Yeah. I guess so. Yeah, we can't treat like square root of 2 or something in the power. So the fact that k is rational, you can write it as a over b with b not equal to 0. And in some way, you're going to use that fact to prove this power rule. Theorem 2.10. We get derivatives of constant okay, so we get kf. Oh, and now just out of nowhere we're switching to prime notation. Kf prime is, you can take out the constant for any function. So like Yeah, I don't have good examples right now. I don't know. 2x squared, the derivative is going to be the same as, I'm going to use Leibniz notation because I'm on Team Leibniz, y'all. We can pull out that constant, that scaling number 2 that just multiplies every value by 2. We can pull it out of the derivative and then calculate 2 derivative of x squared. And then, based on this last theorem, the power rule, we can then we can calculate this as 2x to the 2 minus 1, which is just 2x. So, the derivative of 2x squared is 4x. And the important part that I'm showing right now is that you can bring out a scalar multiple out of the derivative. Then what else do we have? We have the sum rule. If you have two functions that are added, you can add the derivatives separately. An example of that one, oops, I wanted a different color. An example of that one using the, again, using the power rule, which we just proved, or didn't prove, but stated without proof, is that the derivative of this is going to be the derivative of the first term, the first function that is added. Oops. I got ahead of myself. And then now we can, by the power rule, say that this is 3x squared plus 2x. And that's an example of a composition of functions by adding them together. Yeah. Next we have the difference rule, which is really the same thing. F minus g, it's just that we're adding a negative instead of a positive. You could also think of this third piece as a combination of 1 and 2. 1 and 2 imply 3, where k is -1 for the second function g, if you do want to prove it for yourself. But right now, we're just going to put on our engineer hat and skip all the proofs and just try to get to Mars as quickly as we can. Theorem 2.11. Derivatives of products and quotients I think with this one, we're going to be pretty close to done. I think in another section, there will be derivatives of trig functions, and I think I'll just skip those for today. I want to get to those differential equations that I mentioned. So if we multiply two functions together, and take the derivative, we get this. my shorthand notation, just so that I can rewrite this for myself, is fg prime equals f prime g plus fg prime. This is my little shorthand cheat sheet way of remembering the product rule. It just, yeah, we're removing the point x from everywhere, or just reminding ourselves that it's a function evaluated at a point, but we still have f prime without, and then the original function g, and then the original function g times g prime. It's the same as my shorthand right here, even though this is not fully rigorous or defined what I mean by this yet, but you can define that. Now, quotient rule. This one, I don't like memorizing this. I just don't like memorizing it. I don't think it's worth it. But it is this. F prime x g of x, and I'll show what I mean by that, minus fx g prime x. This one is, to me, I don't know, my simple brain always gets confused trying to remember, is it g or is it g that we square in the denominator, and like what order do we do the numerator? Is it f prime g minus f g prime, or is it g prime f minus f whatever? I'll show what I mean, but first let's get shorthand notation so that if you do want to memorize this formulation, it's this. So there's the shorthand. If you have two functions that are divided, a function divided by another function, and then you take the derivative of that composition, then the derivative of all that is that thing. F prime g minus g prime f over g prime squared. The mnemonic that I learned in high school was low D high minus high D low over low squared. I don't know why that has stuck in my head. Low D high minus high D low over low squared. So maybe that'll help you. But what I wanted to show is that you could also think of f over g is the same thing as f times g inverse, right? Because dividing by a function or dividing by a number is the same as raising that thing to -1. Then if we believe the power rule, by the power rule, and product rule, if we believe both of those are true, as well as the inverse thing that I just said, So here is an application of the product rule. And again, the prime apostrophe thing means take the derivative. Now, if we believe the power rule, then this is negative 1 times g to the negative 2. Somehow this is easier for my brain to always just rederive the to rederive this quotient rule. But you do you. I mean, if I would stop somewhere like here, but if we want to convince ourselves that it's the same thing, we can rewrite those -1 powers as divisions. Is this still working? Did I get this wrong? I think I got something wrong. So, yeah, I think I got something wrong because right now what I have is f prime. To get a common denominator, we need f prime g over g squared minus f over g squared. So you know what? Just don't listen to me. Don't learn math from me. I don't know what I'm doing. F prime g minus what I just got was this, and that's not right. So we are missing right now the g prime right there. I think we need chain rule as well in order to get this to work, this approach. Yeah, we need chain rule, don't we? Yeah. There should also be another g prime right here. Yeah, we need chain rule, so don't worry about it. I think that would be another theorem or something that this person does. Let's just keep this original definition or this original result, the quotient rule. Low d high minus high d low over low squared. And that's it. Those are all the theorems well, we may need this one too. We may need chain rule. And this is a theorem. It is not a definition. It's something that you can prove. The chain rule on okay. There's a bunch of words and they look really nice. It's very precise and written well. Go buy the book and read it yourself if you want to understand it. But if you're like me and you're reviewing this and you've previously learned this in the past, you may know exactly what I'm talking about right here. Okay, so in short, this is suppose I don't know if we've done any problems or shown any examples of a composition of functions. And I know that some people in the audience are at more basic math. So I think it would be really good at some point to show an example of composition of functions. But in our differential equation, yeah. You may have seen e to the x, and we'll get there later on in calculus. This is a transcendental function. That's similar to e to the 2x. This function can be thought of as e to... It's a composition of the two functions. So, like, if we replace the x in this function, it's like if we plugged in the other function u into f. If we plugged in u and replaced every x in this function with the value of u, or the function u, then this is a composition of two functions. Yeah. And so, here, in trying to derive the quotient rule, my mistake was saying that the derivative of my mistake was saying that it was going to be negative g to the negative 2. What I was missing is, and here I was treating, this is getting so confusing. I have g, f, u. I'm considering the function x to the minus 1, but here we're plugging in the function g of x into that simpler function x to the minus 1. So this is like f of g of x. So the derivative of that, according to the chain rule, is going to be f prime evaluated at g of x times the derivative of the composed inner function. So what we needed to multiply by here is g prime. And I missed that. Cool. You with me? Probably not. Let's move on. I think those are all of the facts that we need about the derivative that I am going to need if I'm going to try to help us get to Mars. So let's get this book and let's solve a problem or two. I just wanted to do maybe... Where the heck do I have these written? I don't feel like reading Tenenbaum 1.1 today. I just want to jump to the math. let's just work this problem. 1.4, oops. You've got several equations here. Some of them we can do, some of them I'll just do without proof. Yeah, I think we only have enough machinery. No, we don't have enough machinery for any of these, because we do have e to the negative x, and I haven't shown that one yet. But whatever. Let's just do it anyways. I'll tell you what that is. Oops. All right. So here's Tenenbaum 1.4.1. Let's give us some space for that. And what I am going to show is that this function satisfies this equation. Hey, Paolo, I'm doing really good. Thanks for stopping by. Hit the like button. Hit the like and subscribe button. You've been here before, right, Paolo? Maybe you're already subscribed. I introduced the derivative, and now I'm trying to solve a differential equation. So no lecturer in their right mind would do all of this in one lecture. So that's where I get to just be a hobbyist and be like, meh, whatever. I'm just gonna jump right into saving the world or whatever with differential equations. We're gonna get to Mars slowly but surely. That's a stupid joke. I should stop saying that. It's getting annoying. We get it. I used to study pure math, and so I'm looking forward to just learning some applied math. So, if we want to see that the function on the left satisfies the equation on the right, then, well, we need to find out what the second derivative is. I didn't show any examples, but 2 primes just means take the derivative twice. So do 2 derivatives. So if we do 1 derivative, let's do this slowly. If we do this very slowly, then it would be meh. All right. So I'm going to go ahead and assume, and you can check for yourself, that the second derivative also follows the sum rule. Is that what it's called in the book? Sum rule? Difference rule? Something or other? We defined the derivative. We got some simple derivatives of lines. We have the power rule. And then sums, sums of functions. So the derivative of a sum of functions is the sum of derivatives. Okay? I'm going to assume without proof that doing the derivative twice also follows the sum rule for the sake of time. Then we have a constant, whatever it is, and the derivative applied twice, plus the derivative of this twice, plus the derivative of this, x cubed over 3, twice. Okay, taking the derivative of a constant is 0. We found that already. So I'm just going to cross it out. And then if we take the derivative once of the second term, we can use the constant rule, the constant rule, I suppose, to say that this is going to be two derivatives of this thing, and also a constant rule on this one. By the time you're taking differential equations, you probably don't need to write out every single step like this. Like, you could probably write down the derivatives of some of these more quickly, but I think it's cool to try to show how the derivative is useful. Like, I defined the derivative, and now I'm claiming that the real world is all about solving some of these differential equations and seeing when you can plug in, like, what functions satisfy some differential equation. I don't know, that's my understanding. So anyways, so here we need one last derivative fact, which is that e to the x, which you've probably seen, I apologize if you haven't, it's an exponential function with a special number e, and the special number e is, by definition, the one number e such that the derivative of e to the x is e to the x. For other bases, we don't have such a nice derivative. So that is where the Euler number e comes from. It is the special number such that the derivative of e to the x is still e to the x. Then here we have a chain rule that we need to apply. So this is going to be so the derivative of the inner function, the composed function, the derivative of negative x is just -1. We can see that from the power rule. So this is going to be -c2 times e to the negative x. We've taken one derivative so far, so we have another derivative left to do. And then here we have 1/3 times 3x squared if we do one derivative, and then we have one more left to do. Okay? Again, the derivative of e to the negative x is going to be -e to the negative x. We'll write that out explicitly. The derivative of e to the negative x equals -e to the negative x by the chain rule. Then this is going to be c2e to the negative x. Here we can take the scalar multiple rule to pull out that 3 out of this derivative, and then the 3 and 1/3 cancel each other out. They just multiply to 1. So all that we have left is the derivative of x squared, which is 2x. Okay? So now we have found y double prime is equal to this. Okay, so we're getting somewhere. We found a double derivative of the function on the left. And I suppose I could have found one derivative first, and then we would have been done, but let's do it all over again. Y prime is the derivative of c1 plus c2 e to the negative x plus x cubed over 3, the derivative of all of that. So I'll move quicker on this one. This is going to be negative c2 e to the negative x plus x squared. So think of it as the sum rule. The derivative of the constant c1 is 0. The derivative of the second term, again, we have a chain rule. And then the derivative of the third term, we use a power rule and a scalar multiple rule or something. Now we have y prime. Oops. We have y prime, and then we just need to subtract this stuff. So finally we get to the really awesome part. Let's see what happens when we plug in y double prime and y prime minus x squared minus 2x. Y double prime plus y prime minus x squared minus 2x minus x squared minus 2x. What does that equal? We found y double prime is c2 e to the negative x plus 2x. We found y prime is negative c2 e to the negative x plus x squared. So I substituted y double prime and y prime. Now we still have the x squared and 2x terms. Minus x squared minus 2x. Okay. Well, c2e to the minus x minus c2e to the negative x, those two cancel each other out to 0. And now we have 2x plus x squared minus 2x. I think we can see that these terms cancel each other out, and these terms cancel each other out, and it equals 0. As desired, QED, boom, we're one step closer to landing on Mars. All right, so let me answer your question. I'm sorry that it took me so long to answer it. Paulo, hey, I just have a quick question. I'm thinking of taking abstract algebra this coming semester. Abstract algebra. Congratulations. You're going to love it. I loved it very much. Beautiful math. It's like playing chess. Of taking abstract algebra this upcoming semester. However, after taking discrete math last semester, I don't feel very comfortable with proofs. Should I wait and take it another time? Yes. I would say yes. It depends on what your abstract algebra course is, how it's structured. I learned from Baby Hungerford. I learned my first course in linear was in this textbook. There are two Hungerford textbooks. One is scary and it is hard. That is Hungerford. Baby Hungerford is for undergrads. And my course was called Intro to Proofs and Abstract Algebra. So at my university, we taught intro to proofs in that course. So half of the course was intro to proofs, and half of the course was abstract algebra. So if your course is like that you're looking at in your syllabus, then I would say go for it. Yeah, sure. If it is your intro to proofs course and you will be learning proofs in that course, go for it. But the fact that you said that that you took a discrete math course, was that from the math department or was it from the computer science department? At my university, the CS department had a discrete math course, but the math department did not have a discrete math class. The math department just did this class, Intro to Proofs and Abstract Algebra. The fact that you said that there was a proof-based class where you learned proofs. Okay, it was from the math department. Great. So then I would try to find out what textbook does that abstract algebra class, what textbook have the recent semesters used? You could ask the other students, maybe you have friends in higher grades, or you could email the teacher if you know which teacher is going to teach the next semester. If you could get a hold of the syllabus of what text they plan to use, I could answer your question better. Because I totally think that you can learn proofs in Baby Hungerford, but I would run far away and say, yes, get better at proofs. Get better at proofs before, if the textbook is, here's a common one, Dummett and Foote. This is like one of the most successful, most famous abstract algebra texts. It might be Artin. It might be, what are other common ones? I don't know what else. I don't know why I'm blanking. I mean, yours is not going to be taught out of Lang, like you would know, I think. Oh, and your professor has her own book. Cool. Well, then I would definitely ask the professor, like, how comfortable do you think someone needs to be at proofs for your textbook? Ooh, algebra, pure and applied. That sounds cool as hell. Okay, so I'm going to say yes or probably. Go for it. Ask her, though. That sounds really great. Algebra. I want to get that book. Like, whenever we do start abstract algebra series here on this channel, that sounds great. Pure and applied. Because clearly it's going to have some proofs and some applications, right? I mean, I'm just assuming based on the title. So I would say go for it, personally, and especially if you're here and showing up to these streams, I can help you learn proofs. Like, we're going to be practicing proofs here, and you can, hopefully we can have like a little study group. I say go for it. Abstract algebra is beautiful. It is like getting really good at chess or something. And I keep saying that, and it's nonsense. It's honestly nonsense. I'm making stuff up because I'm trying to say that usually abstract algebra is taught abstractly, and it doesn't feel like it's useful. Like, getting good at chess is kind of pointless, but it's fun and it's beautiful and it's worth doing. But it can feel very pure, quote unquote. And it feels like one of those maths that's like, this can never be used in the real world, but actually it's extremely useful, and used all the time in a lot of modern mathematics. So not just applied to other mathematics, but also applied to things like cryptography, which heavily requires abstract algebra and number theory. Abstract algebra is also used constantly in physics, like, or chemistry even, when you're understanding the symmetries of an object. Like, symmetry is really important in physics. So that sounds really cool, and I would love to learn that. I can help you with your class. Like, I'll help you cheat on your homework and like work through that book together. Because I want to learn more applications. I studied pure math in my undergrad, and it's beautiful, and I love it, and I don't regret it. But nowadays, I'm a little bit more interested in applications. So I say go for it, probably, but ask your teacher, and we will be getting better and better at proofs in this YouTube series. I think that I'll be working through this book, How to Prove It, in my number theory series. So I say number theory, like learning number theory or practicing number theory, but really that is going to be proof-based mathematics, learning proofs, and because you can't really do number theory, you can't really study number theory, I don't think, without proofs. Like, so we'll be learning proof techniques in that series, and we can work through this book together and get better at proofs. So, I don't know. Nobody ever feels comfortable with proofs. Like, did you get an F? Did you fail discrete math? Like, yeah, maybe take discrete math again and don't fail it. But if you got a B, I'd say definitely go for it. Don't worry about it. Like, you probably have a lack of confidence in your proofs, because everybody does. It takes a lot of practice. It takes a lot of courses until you start feeling good at proofs. So I don't know. You tell me. If you got a C in that course, maybe, maybe not. I don't know. I can't tell you without doing like a private lesson one-on-one, which, hey, themathhobbyist@gmail.com, private lessons. I could be your private tutor. All right, so you got a C plus. Then you're borderline. I would need to test you, and we would work together. But I don't know, man. I think that you could, from what I can hear, I think that you might be ready. And you, like, at least in my university, we taught proofs in an abstract algebra class. So, I don't know. Book a private lesson with me. Email me. Email is below. First one is free. Following ones are relatively cheap. And I could help you answer that like a little bit better. But for now, I want to do another differential equations problem. Cool. So, starting on Sunday, tomorrow's going to be SAT math, easy basic math. And then on Sunday, we're going to start the next number theory week. So every week, I'm jumping around 3 different subjects: number theory and proofs, linear algebra, and applications mostly, and then calculus. All of these are going to have some proofs and some applications. But yeah, next week is number theory, and I'll start looking at that How to Prove It book, and we can work together on it. Yeah, so my answer is probably go for it, but maybe, I don't know. Book a private lesson. First one is free. Cool. All right, so we solved one problem, and I feel great about it. We have officially done one differential equation problem. I feel great. We did Tenenbaum. What is it again? It doesn't matter. 1.4 1 through 3. That's what we're solving. Tenenbaum 1.4, problems 1 through 3. Number 2. I copied it right here. Yoink. All right, so that's number 2. Let's give ourselves some space for number 3, and then this time we're going to solve it a little bit more elegantly. Oh wait, what? We already did this one, right? Oh no, we didn't. 2 is just similar. It looks a little similar to 1. Yeah, but it's not. It's not at all the same. What am I talking about? All right, so we have y. We're going to need to get y prime, and we're going to need y double prime. So this time around, we're going to... Ooh, yeah, you recently got the Art of Problem Solving book. Yeah, I hear that those are very good. I've never looked at them myself. But, yeah, I've heard that those are good. Okay, so this one we're going to do a little bit more quickly. We're going to get negative 2c1 e to the negative 2x minus c2 e to the negative x plus 2e to the x. That's y prime. Y double prime is going to be the derivative of y prime, which now, taking the derivative of this last line, we have 4c1 e to the negative 2x plus c2 e to the negative x plus 2e to the x. Okay, now we have all of the pieces that we need, so we can start chipping away at this. I'm going to start with the left-hand side. I'm just going to rewrite it for funsies. Y double prime plus 3y prime plus 2y minus 12e to the x. That equals, substituting y double prime, 4c1 e to the negative 2x plus c2 e to the negative x plus 2e to the x. Let me give myself some more space, because I don't... Well, whatever. Who cares? All right, now we have 3y prime, negative 2c1e to the negative 2x, minus c2e. This is nice and meditative. It's very calming. I get to relax and focus on my breath for a moment while we just write out, copy things again and again. Now we substitute in y. C1 e to the negative 2x plus c2 e to the negative x plus 2e to the x. I should ask Paulo, a better, more nuanced answer would be, what is your goal? Like, do you want to be a mathematician? Do you want to study math or maybe something similar like physics? Or do you want to become an engineer? Those are the most common reasons that people study math. Like, you want to become an engineer, or you want to become a mathematician or scientist. I don't know. Yeah, like if you want to become a theoretical physicist, I'd say go for it. Yeah, take that abstract algebra course. Or if you want to complete like a math minor or a math major, I'd say go for it. Like, you can learn it. Just based on the title of that book, I think it's going to be fine. But I could be completely wrong. Like, 2 books can be completely separate. 2 courses titled the same thing can be completely different. So it depends on the level of maturity, quote unquote, that this professor is expecting. There's probably like a course description that will say what level of math maturity they expect. I don't mean that in any kind of derisive way. It's just a term that says, like, how comfortable are you with proofs? How comfortable are you with problem solving? Very true about chess. A master of chess is a wasted life, quote unquote. Exactly, right? That is a famous saying from like some chess grandmaster, I think. Like, a master at chess is a wasted life. Quote unquote wasted though, because like, they had fun. They had a nice life in a lot of ways. Like, they didn't like advance, humanity's understanding of the world, or they didn't like help us get to Mars, but they also didn't hurt the world, right? There's a fantastic book about this called A Mathematician's Apology. Incredible book, very sad, a little bittersweet, by this guy, pure mathematician Hardy. And in this book, he's really just reflecting on his life, and he feels like he's accomplished nothing, quote unquote, that he's had a wasted, quote unquote, life. And he's kind of just reflecting on this, like, I have done a lot of mathematics that will never be useful in the real world in any way. Did I waste my life? And the answer is no. The answer is like, no. Actually, like, I studied some beautiful mathematics. I made advancements. It's okay that it didn't help save the world. It's okay that I didn't help save the world, because at least I didn't contribute to destroying the world. Like, at least number theory is not going to create a nuclear bomb. In his mind, number theory was completely useless, like chess. But at least he didn't help create the atomic bomb. Joke's on you, dude. You helped create Bitcoin. All right, let's keep moving on. So, we plugged in 12E. We have... Yeah. All right, so I've already substituted y double prime. We helped substitute in y prime, and we helped substitute y. Now we just need to collect terms and combine terms. So if I look at these terms that all have e to the minus 2x, I can see that those I'm going to combine. So here we have 4 minus 6 plus 2. Well, that's 0. 0 times C1. We'll make it explicit just so that we prove to our teachers that we did it right. Right? And we can see that term should be 0. Next, we're going to collect our, I don't know, maybe we do this in another color just for funsies. We have C2 minus 3C2 plus 2C2, right? 1 minus 3 plus 2 C2 e to the negative x, right? And then next we're going to collect all these terms with e to the positive x. And we can see we've got 2 plus 6, 2 plus 6. 6 is coming from that 3 distributed through. 3 times 2 gives us that 6. Plus 4. And then we have a minus 12. E to the x. And now we've grouped everything together, and voila, as we desired, we have 0 c1 e to the minus 2x, plus 0 c2 e to the minus x, plus 0 e to the x. And voila, we have 0. QED. Boom. Problem 2 done. Hey, Punith. Oh, wait, it's morning. Sorta. I mean, for me, it is 10:39. I've been up for a few hours. A couple of hours or so. Ooh, Paolo. I wanted to get into the quantitative side of finance. Abstract algebra, I don't know if it's the most directly applied, although it might be. So if your goal, I would say that your goal should be to get good at problem solving. If you can get good at problem solving, then you can get into a quant role. And abstract algebra will help stretch your mind. It'll help you get really good at problem solving. You may not use abstract algebra in your day-to-day, and that's okay. I think it would be very helpful for you. But if you really want to get into quantitative finance, I think that what I'm doing right now is more applicable in the day-to-day, like solving differential equations and calculus and analysis, doing that branch of math, like studying calculus and differential equations, you're going to use daily. But I think learning abstract algebra and number theory would be very helpful as well. And getting any kind of math degree. I would say if you want to get into quantitative finance to stand out, I mean, you're not going to be standing out. Most people, I think, who do quantitative finance are going to be coming in from a computer science and math background. Most people have a math degree if you want to become a quant. And if you want to get a math degree, you have to take abstract algebra. So, I don't know, it's up to you. You could do it this semester or next semester. You could learn some proof techniques here through this stream or private lessons or whatever. But at some point, you'll want to take that class. Yeah. Cool. Last one, and then I think I'll call it a day. Y prime is going to be C1 minus C2. Okay, we need a new fact. New fact without proof. The derivative of the natural log of x is 1 over x. And in a lot of math textbooks, in a math textbook, log means natural log. This is the same thing. Yeah, in other textbooks, log means base 2, but this is a math book, so log means base e. And it's the inverse function of the logarithm, of the exponential function. So if you take the logarithm of e to the x, you get x, and e raised to the natural log of x is also x. So inverse function. Yeah. All right. So if we assume that that's true, now here we're going to do a product rule. Remember that the derivative of a product looks like this. And again, you can quote unquote pull out a constant. So the derivative of the first term x is just 1, and then we keep the second function log x the same. And then we add the first function, unscathed, untouched, times the derivative of the second function. Derivative of log x, again, is 1 over x. And I'm stating that without proof. So simplifying this, log x over 2 plus, so x divided by x, this term is going to be 1. And so here we have all of this. Now y double prime, so the derivative of y prime, we're going to get 0, 0, 1/2 times 1 over x, and then the derivative of 1/2 is 0, so this is 1 over 2x. Now we can start chipping away at the right-hand side to see that it equals 0. X squared y double prime plus xy prime minus y minus x, that equals x squared times the second derivative, which we just found was 1 over 2x, pretty easy, x times the first derivative, which we found was c1 minus c2 plus log x over 2 plus 1/2. Okay. Now we have a minus y. So we subtract the original equation. Y is c1x plus c2x inverse plus 1/2 x log x. So that's our minus y term, and then lastly we have a minus x in this differential equation. All right, now let's just do some lovely mindful math. Just some algebra, collecting terms and whatnot. So now we have x squared, or x over 2 plus c1x minus c2x plus 1/2 x log x plus x over 2. So I distributed that x through this term. And now we're going to subtract all of these, c1x minus c2x inverse minus 1/2 x log x. And then we subtract x. Okay, so I want to simplify this. And I want to I don't know. I feel like we'll make a lot of progress if we take a look at the most complicated terms first, maybe. X log x. I'm going to see that as 1/2 x log x minus 1/2, x log x. Exactly how we wanted. So that term is going to be 0 x log x. Now, let's collect our x terms. So here we have 1/2. Here we add a C1. Here we subtract C2. Here we add a 1/2. Here we subtract a C1. Here we subtract a C. Oh, wait. Oh, that one is X inverse. Yeah, so there we subtract C1. Did I screw something up? I hope not. Did I? Something's feeling wrong. C2 terms aren't canceling out, are they? Okay, well, we'll find the mistake, I think, and that's fine. So C1 minus C2, I've already underlined the terms that I've written down, I think. X over 2, C1x minus C2x. X over 2 is at 1/2, and then minus C1 minus x. Right? And now the only thing left is x inverse. So I think I messed this up. Okay, so we got 0 x log x as we desired. And now here, this 1/2 plus 1 minus 1, that's a 0. C1 minus C1 is a 0. So now we have minus C2x. Minus C2x inverse. So, okay, so something went wrong, unless, number 2. So I think it was like a chain rule problem somewhere. Thank you for responding to my questions. Of course, thank you for bringing the questions. It's fun to talk with fellow mathematicians. All right, let's go back and double check our derivatives. The first derivative. Oh. Yeah. Oops. This should have been this part right here. This should have been minus C2 x to the minus 2. I did that, yeah, I did that wrong. So this should have been x minus 2. How do we want to fix that? I think that would cause all of the problems that we just hit. Okay, so let's use another color to make sure that we carry this through everywhere correctly. Yeah, the derivative of C2x inverse is minus C2x to the negative 2. When I was writing that, I was like, something feels wrong that I have two constants in a row. Okay, so C2x to the minus 2. And then y double prime should have been negative 2x to the negative 3. Right? I'm just gonna rework this problem, y'all. We screwed this up. Take 2. Take 2. This time I'm gonna get rid of Alright, so I'm gonna assume those things without proof. I'm not going to restate the assumptions. Yeah, sometimes when you make a mistake, it's just better to just start over. Don't try to like fix it. Just go back, take the moment. It's not going to be a big deal. Sometimes it's easier to just do it over again. This was kind of pointless. Why did I like duplicate everything? Again, like sometimes it's easier to just rework it, just write it down again. Oops. Okay. That's fine. Y prime. So the derivative here is C1 minus C2 x to the negative 2 plus 1/2 times x over x plus log x. C1 minus C2 x to the negative 2 plus 1/2 plus 1/2 log x. Okay. Second derivative is going to be 2c2 x to the minus 3 plus 1 over 2x. Then x squared y double prime plus x y prime minus y minus x equals x squared times 2c2x to the negative 3 plus 1 over 2x plus x times y prime, which we found to be c1 minus c2 x to the negative 2 plus 1/2 plus 1/2 log x. That was x, y prime. Now we need to subtract y in this differential equation right there. Minus y minus x. So minus c1x plus C2 x inverse plus 1/2 x log x. And then we subtracted x. Let's collect terms, or distribute 2c2x to x inverse plus 1/2 times x. Yeah. Plus c1x minus c2x inverse plus x over 2 plus x over 2 log x. Minus c1x minus c2x inverse minus 1/2 x log x, and finally minus x. Whew. Okay, so this thing is getting kind of gnarly. Again, it's gonna. Oh, son of a. Am I still. Oh, no. Okay. Yeah. So here we have x log x minus 1/2 x log x. So here we have one. If we're collecting all these terms just to write out that we got them all, x log x. What's the next most complicated thing? I would say the next most complicated thing are these x inverse terms. So 2c2 minus c2. I am almost done. 5 minutes. 2 minutes?
Can you pause for a second?
Okay, yeah, sure. Okay. Alright, I have to pause for a second.
I have my therapy.
Okay, so I got 2 minutes to finish this. We are so close, y'all. We are so close. Alright, so 2c2 minus c2, and then another minus c2. These are all the x inverse terms, and then maybe in cyan, I don't know. All the x terms, we have 1/2 x plus c1 plus 1/2 minus c1 minus 1 x. Cool. And that's it. Now we are done. We see that we have 0 x log x plus 0 x inverse plus 1/2 plus 1/2 minus 1, c1 minus c1 is 0x. And then we're done. Boom! Another differential equation solved. Thanks everybody for watching. It's not so much solving a differential equation as verifying a solution to a differential equation, if that makes sense. Cool. Thanks for watching. My name is The Math Hobbyist, and we are done. Again, I am available for private tutoring if anybody wants it. Another way to say thanks is just you could buy me a coffee at thanks.themathhobbyist.com. Or you could just let me know that you enjoyed this. Literally, that is free. Drop a comment below, and let's build a fun math community, y'all. Yeah, thanks for watching. Like and subscribe, drop a comment, drop a question, etc. I'm on almost every day. Thanks for watching. Bye, everyone. Bye.